So today I'm going to be talking about distributed graph processing with Scala and Akka. Please let me know if you can't hear me or anything. I'm running on 0 hours of sleep. I hadn't anticipated there being a hackathon at my company last night, so I'm running on 4 or 5 cups of coffee. Yeah, so let's get started. A little bit about me. I'm a 4th-year student at UC Santa Barbara, where I study in the BS-MS joint program in computer science. I'm also a research assistant on campus, where I study large-scale graph mining and modeling and cluster computing, which is how what I'm going to talk to you guys about today sort of came about. This summer, I'm an engineering analytics intern at Box, where I am using Scooby. I'm doing some stuff, some MapReduce jobs to do some machine learning, and my abstraction of choice is Scooby. I play with sculling a bit, ended up going with Scooby mostly because I like the abstraction better. I've been using Scala since January 2012. I got into it purely because we needed a distributed graph processing system, and at the time, I knew Python and C++. Python was too slow for us, and I would rather not write a distributed system in C++. So I picked up Scala, and so that's what we're going to talk about today. An outline, I'm going to talk about the motivation for why I built it, a little bit about the context and assumptions. The system was designed specifically for my lab. Our lab has a very specific set of requirements, and I wanted to build a system that made our job as easy as possible. I'm going to talk about the user and system requirements I had for a system. The solution, show you a lot of code, and then hopefully, assuming nothing goes wrong, I'll show a little live demo of the system running on a lab cluster. So the motivation, let me pull up these notes here. Okay. So the motivation, a lot of our algorithms are embarrassingly parallel. And so Google does have this Prego model for graph computation, but it has this different view on things where it says you think like a vertex and you think at each super step I'm going to receive messages from other nodes, and then I have to think about what messages I'm going to send to other nodes and how all of that adds up. And while that would probably work for us, we wanted something simpler. We wanted to just be able to write the algorithm, tell it what sort of input the algorithm took, and then have magic happen and have it distributed. So for example, in shortest paths, for an unweighted graph, what we would do is just give each worker one node at a time, and then we would just run a simple breadth first search and then return a mapping from a destination node and the shortest path. So we didn't want to go through the trouble of thinking, OK, at this step, I'm going to send this to the other nodes. I just wanted to write a BFS and then distribute the work based on at a node level granularity. Some context and assumptions specific to our lab. We are studying large-scale static graphs, and these graphs are usually from online social networks. So you can think of each person being a node in the graph, and then a friendship or a follow being a link between two people. We have a cluster of around 30 machines. The cluster shares a file system. I believe it is a network file system. Graphs are very large. They go anywhere between a few thousand nodes to a couple million. That's probably tiny compared to what Facebook deals with, but it's not a trivial amount of nodes. But our machines have enough memory to fit the entire graph into memory. So we didn't want to keep doing some fancy loading and dumping to disk. We just wanted to keep it in memory and compute on that. And we also wanted raw results dumped to disk. So for example, if we wanted to find the degree of all nodes or something, we wouldn't reduce it down to like the average degree. We would literally just dump to disk a file mapping a node and its degree, and we would just have one massive file. And then after that, we would take it into something like Python and then do whatever analysis we wanted on that raw data. Some user requirements I had for a system. The users should not have to deal with Akka. I was building this system with some for some PhD students to use as well, and they didn't have much experience with Scala, and I didn't want them having to worry about, oh, I have to first spawn this master actor and then to worry about I'd spawn these worker actors, anything like that. It should have been really easy for them to get a job running. They should only have to define the algorithm input. So like I said earlier, just define a BFS and define that I want the work distributed on a per node granularity. They should be able to put an upper bound on the number of threads per machine. We don't really have a schedule in a cluster as of now. The way we sort of work is maybe a student right now is doing some data analysis on this machine and say, OK, I'm going to only deploy maybe 2 worker threads on that machine, and that frees up some threads for the other students to do analysis on. Some of the system requirements we had, we should be able to deploy without any previous cluster setup. We have NFS. We didn't want to have to install HDFS or Hadoop or Hive or anything like that, any complex configuration. We needed to be fault tolerant, of course. If a worker died, the whole system shouldn't go down. We want to be elastic, meaning if at some point in the middle of the computation, some machine freed up or we added a new machine to our cluster or whatever, I should be able to just spawn a worker on that machine, point it at the master, and have work distributed to that new worker without having to shut down the master or anything. Graphs should be loaded locally. What this meant, and this was probably obvious, but the very first iteration of the system I built when I had about 2 months of Scala in me was that I had made the messages sent to the remote actors such that the graph was packaged with each node, and that was obviously a complete waste of network resources. At this point, because all the machines are sitting on NFS together, they should just be able to load their own copy of the graph and keep it in memory. And then the only thing that would be distributed around is the work, so like a per node or a pair of nodes or whatever. And the whole system should clean up after itself. There shouldn't be there's no like Hadoop job tracker or anything. We're launching this on a per job basis. If we want to do average degree, then we spawn one single instance. If we want to do page rank, we spawn up a separate instance. No central job coordinator. The inspiration for this, there was really good timing. I was designing the second iteration of the system around summer of last year, I believe. And that was when the Akka team was holding its Summer of Blog competition, where people were supposed to submit blogs in regards to Akka, doing something cool with Akka, submit a blog. If they liked it, they published it. And this guy called Derek Wyatt had published a post called Balancing Workloads Across Nodes with Akka 2. And this was precisely what I wanted to do with my system. I wanted to have a central master, balance workloads across several workers, and it's very simple to balance because the work was all the same. Each worker would get a node, finish, get another node, so on. And so I wrote a follow-up post to that called Distributed In-Memory Graph Processing with Akka, which basically took his system, which was more of a general description of a generic master worker system, and I added some few things and changed a few things to make it specific to my use case, which is in the context of graphs. So basically, his blog post and what we wanted was he described the idea of a balancing dispatcher, right? So Akka comes with this idea of a balancing dispatcher for local machines, where you have like the central mailbox backed by several actors, and then when you send a message to that mailbox, that proxy mailbox would handle sending that message to an idle worker. So that's basically what he wanted. As messages came in, it would target only the idle workers. As the workers finished, new messages would be sent to them, if there were still messages to be sent. Yeah, I talked about this. So yeah, this is basically how it works, right? We have a balancing dispatcher. We have a mailbox. As workers are idle, messages get sent to them. Once they're working, if new messages come in, it will either sit in the mailbox or wait until some other actor becomes idle. Once the actor becomes idle, they get the new message, so on and so forth. We wanted this at the remote level, so across several machines in our cluster. And so with the actor model, this is really simple, right? Basically, we have a single master, which represents a dispatcher that stores all the messages inside some sort of like a queue or a list or something. Each remote actor or the worker has its own mailbox, and then once it's idle, it will send a message to the master telling it that I need more work. The master will give it work. It will begin computing, and once it's done, it will know when it itself is done, and then it will send the master saying, okay, I'm done computing, give me more work. And so this becomes a very easy implementation in terms of the actor model. Some design decision that I had to make was, so Akka is capable of doing remote deployment and remote lookup. The benefit of remote deployment is that if the master deploys the worker, the master, by definition, now knows that the worker exists. Remote lookup, the benefit of that is that the downside is the master doesn't know the worker exists until the worker registers itself with the master by sending in a message. But the positive side to this is that like I discussed earlier, when we added a new machine to a cluster or a machine freed up, I can just spawn a new worker and point it at the master. And so if we did remote deployment, once the master had spawned the worker actors, there's no easy way to get it to spawn more actors on other machines. And so I decided to go with the remote lookup method, and that actually worked out really good. So basically, this is how it works. We have the master. The workers will register with them, will send a message to the master. At that point, the master has the actor reference to that remote actor. It will save it inside some sort of queue in its internal state, and then from there on, it can do the whole balancing dispatcher thing. The overall design of the system is pretty simple. We have the outside world sending in some sort of work to the master. The master will queue up the work. As workers spawn, it will tell the master it's idle. The master will send the worker some work. The worker will go into some sort of busy state. Once it's done, it will trigger some sort of event to make it send another message back to the master. The master will notice it's idle. If there's more work, it'll send it back to the worker, so on and so forth. And so now I'm going to start showing some code. Basically, I'm going to show a majority of the code it takes to implement the master and the worker. And then I'll show a full application using what I call this, the name of the system, I call it Sabre. I'll show a full application of Sabre, and then hopefully I can show a live demo, and then we can finish off. So these are the messages that the master receives, right? So from the outside world, it will send a message to distribute work containing the work that it wants to distribute, so maybe like a single node or a pair of nodes. There's another message that the outside world can send to it called all work sent that basically tells the master, I'm done with the work, and that's how the master knows that once all the workers are idle and all the work is sent and our worker queue is empty, then we can begin to clean everything up. A worker can also send messages to the master, of course. You get the worker created message. That's how the workers tell the master of its existence, and that's when the master stores that worker's actor ref inside its internal state. The worker can also request work from the actor. This usually happens once the first time it registers itself with the master, as well as when it finishes work. And there's also a work is done message that serves a similar purpose to worker request work, and we'll see an example of that in a bit. So the master, the constructor is pretty simple. We have some notion of an abstract algorithm, and the algorithm is basically a trait that defines a single method execute. The execute method takes in two parameters. One is the graph structure, and one is some sort of input, so maybe a node ID or a pair of nodes. The result handler is where all the results of the computation get sent. So for example, a master will send to a worker a single node ID. The worker will compute the full breadth first search across the entire graph. It will take that map, send it to the result handler, and the result handler can choose to do some sort of reduction on it or just dump that map to disk or serialize it or whatever. And by default, the most common use case for this for us was just literally just printing out a map onto disk. But there were some cases where I did do some sort of reduction. You can also see the two important data structures. Workers is a map from a worker's actor ref to any work it's doing. So it's an option because that worker may be idle or may be doing some sort of work. And the work queue is basically just a queue of any work that's left to be done. So the first message that the master can receive is worker created. It's pretty straightforward. It'll log it. It'll watch it. What context.watch does is basically it subscribes the master to the worker's events. So if that worker were to die, the master would get a terminated message, and then the master can choose what to do with that message. In this case, he would take whatever work was. It would take whatever work that actor was working on, and then put it back in the queue, and then consider that actor dead. So once it receives the worker created, that means this is the first time a worker has contacted the master. So it will go ahead and bundle up that algorithm that was in the constructor, send it to the worker, so the worker now knows what algorithm to compute. And then it will notify the worker. It will call this notify workers function, which basically all it does is if there is work left to be done inside the queue, it will broadcast a message to all workers saying, I have work. If you're idle, talk to me, and I'll give you work. The second message, worker request work, is pretty simple. It makes sure that the worker has registered before. If the work is empty, it just sends back there's no work to be done, and you can sit in the idle stage. Otherwise, If you are idle, then I dequeue something off the work. I put into the mapping that you are doing work, and then I tell you the work that I want you to do. And notice that we're not just doing worker bang work to be done work. We're using this worker.tell so I can do this result handler thing. So to the worker, the sender is the result handler, and so it can automatically use the sender to send back whatever the result is. The work is done message, pretty straightforward. If the worker has never registered before, you log it. Otherwise, make it idle. At this point, if all work is finished, meaning the queue is empty, the all work sent message has been received, that's when the master begins broadcasting messages to tell everyone to shut themselves down. This is the message that the master will get if a worker were to die for whatever reason. Basically, what it does is log the error, get the work that worker was previously working on, and then tell itself to distribute the work. So that triggers that event where it just takes the encapsulated work and puts it back in the queue, and then removes the worker from the map. It doesn't try to do any sort of recovery for the worker. If a worker goes down, then it's down. This event gets triggered when a remote JVM completely shuts down, and that just triggers a function that goes through the entire worker map and sees which workers were on that machine, and it considers them dead, and then requeues the work. This is trivial. You get work, queue it up, notify workers that there's new work to be done. And so if there are idle workers and they're just sitting there, once you get new work, you should wake them up. They shouldn't be sitting idly by just doing nothing and wasting resources. And the all work sent just triggers a simple flag. And then at the very end, if you get some sort of message for whatever reason, you just log the error and you're done. On the worker end, it only ever really communicates with the master. The master will give a do algorithm, it will receive the first time it registers with the master. It will get work to be done from the master after it asks for work. There will be work is ready when the master calls the notify workers function. And then it can also get no work to be done when there's nothing left in the queue. And that's when the actor will idle. The constructor to the worker, so each worker will get its own copy of the graph. It's not sent to it by the master. There's no reason for it to. Everyone's sitting on NFS, so they can see the graph anyways. And then it gets a reference to the master. So that's how it knows to send a message to the master to trigger the registration. You have this case object work complete. That's a message it sends to itself after the work is done, and I'll show you where exactly that's used in a bit. You start out with no algorithm. You just have you hope in the future that you get an algorithm, and if the system works fine, you will, before you get any sort of work. Before the worker actually starts, that's the message that it sends to the master to register itself. So the worker will be in two phases. It will either be working or idle. So inside the default receive function, that is set equal to the idle phase. And I'll talk about how the idle behavior handles messages in a bit. In the case of working behavior, if you're working and someone is telling you that work is ready or there's no work to be done, that's meaningless to you. You have work to do. So there's no reason you should act on those messages. So at some point when you're done computing on your work, you're going to send the worker is going to send a message to itself. That's the work complete message that we saw earlier. In that case, it tells the master that it's done with the work and then requests more work, and then it switches into the idle stage. In the idle stage, this is the default. This is how the workers start out, of course. They get the algorithm. They set the internal state to that algorithm. When work is ready, if they get a work is ready message, that's when they go to the master and ask for work. And if there's when the master gives them work, it first makes sure that they have an algorithm. The system runs fine. There's no reason for it to have no algorithm. I've never seen a case where it's logged that error, but it's good to log it just in case it does happen. This is the interesting part. When it gets something work to do, it calls this do work function. What do work does, instead of actually computing and blocking on that worker, it will spawn off a future of that computation. And At the very end of that future, as part of the future computation, it will send a message to the result handler containing the result. And then finally, it will send itself a message, the work complete message. And that's what triggers the behavior that we saw here. So do work spawns a future that pipes a message to itself. And then there's no work to be done. Then you remain in the idle stage. This is the layer between the whole actor system and the outside world. This is what users will only ever use. They will call saber.execute, give it the abstract algorithm object, and a work, which is an iterable of any. And then potentially, if they want to create their own result handler actor, which I've used before, they can. They can specify their own output file name, or they can just go with the default saber result.txt. A full example of an application looks like this, and that's literally all the code there is, minus the imports. So this is the simple degree algorithm I was talking about earlier, where each worker gets a single node ID, and then it will find the degree of that node and then send it back. So it extends abstract algorithm, it overrides the execute method, and then it simply, inside the graph, gets the node ID, calls the degree method on it, wraps it up in a result, and then sends it back to the result handler. Inside the main object, you define the work that you want. So there's a convenience function inside Saber called from_edgelist.nodes. The user can choose to specify on the command line if they want to write to a different output file other than the default Saber result.txt. And so the general flow of the application looks a bit like this. You have the application on top, which in that last example would have been the degree application. You have Saber, and you have mastering of result handler. So what happens is the application calls saber.execute. That will spawn the Saber actor system. Saber will then spawn a master and a result handler. Once that's all set up, workers can begin spawning and registering themselves with the master. And so they'll have a worker created message. The master will say, do this algorithm, followed by a work is ready message. Worker will request work. Master will give it the work to do. The worker will begin computing in the future. As part of that future, it will send a message to the result handler called handle result. The result handler can choose to do a reduction or write it to file or whatever. It will then send itself a work complete message. And receiving that work complete message triggers itself to send a work is done message to the master. And this can be done, this process is done across all workers. And at any point during this computation, more workers on different machines can be spawned. And they go through the exact same process. They register with the master, and the whole process continues. And so you might have seen in the code that there was a lot of any's. And this is a consequence of Akka being currently not typed. They're untyped endpoints. Receive is, actors are basically a function from any to unit. And so some future work that I was interested in are type channels, which use Scala macros. But I'm hesitant on using them at the moment because macros are in an experimental phase, and I don't want to dedicate a huge chunk of my time to something that may be phased out. So that will be interesting. Akka clustering became finalized in Akka 2.2, and that implements a Dynamo-like peer-to-peer clustering system where you have gossiping and a lot of this cool fault tolerance, and that might be interesting. And recently, they made the type-safe developer console free for developers, and that's basically a really fancy web UI that lets you monitor all the messages being sent throughout your system, the statuses of your various actors, and just all these amazing monitoring metrics that they have, and it's worth checking out. If we have time, I believe, okay, we have plenty of time. Hopefully this will go well. Okay. Okay, so I'm on a remote machine on my lab right now. So does that help? Can people see my code?
Just turn all the lights.
Oh, okay. Yeah. So yeah, I have my build.sbt file. The graph library I'm using is Scala graph, and that's the dependency I use Scala IO to read and dump to disk, and then that is the actual Sabre dependency. I will run the degree algorithm, which outside of those various imports.
Does it just compute the degree of each node?
Yeah.
How do you do the work splitting? Like, how does it make? How do you achieve the speed up?
So the user defines it. So in this case, we're just getting a list of all the nodes. And then we do sabre.execute all nodes. And then Sabre will just take it treats each element of the list as a single. Yeah. And so if you wanted a per node thing, you would group inside here, you would find all pairs or a certain subset of pairs, and then send that to Sabre. So Sabre just treats each element as the payload. So yeah, besides the imports, that was literally all the code that was needed. What I do is I have the SBT assembly plugin, so I build it into a fact jar, this Sabre lab assembly.1 snapshot. I have a configuration file that tells me, let me see if I can make this go away. Okay, I have a configuration file that tells me which graph to compute on, the address of the master node, and then I have a bunch of mappings from worker addresses to how many threads they should use. I also have a short script that basically parses this sabre deploy.cfg file. And anything that's not commented by #, it will automatically deploy. It's a Python script that will deploy workers to those machines. And so first, I'm going to spawn a master. So I believe the script was deploy master. Yeah. So just does sbt run main, gives the class path, and then it gives the output file. So currently, there's no all my degrees.txt file in here. Hopefully, by the end, we'll have that. So I'm going to deploy master. All right, master deployed. I'm going to go into a different screen. And then I have this deploy workers that's basically going to go through that sabre deploy.cfg file and spawn workers on each machine. There's no Python 2.7, so we'll do that instead. Okay, there's a bunch of logging being done. Let's see if I can find where. Okay, so at that point, the graph is small enough that it's finished computing, but you can see that it's getting, workers are registering from Ant-Man, Captain America. Our machines are named after Marvel superheroes. But you can see now we have an allmydegrees.txt file, and if we look inside it, it's just a mapping from node ID to the degree of that node. And so that was just a trivial example to make sure that the code terminated in time. We've done things like the all pair shortest path, page rank, random walk distances, things like that. But yeah, the goal was to get minimal overhead for spawning an application. Hopefully, I've convinced you that that was minimal overhead. And yeah, that's it for my presentation. Any questions?
So basically, the model is that the graph is small enough to be fit in RAM on
Yep.
the machine. So the speed up is achieved by basically thinking of the algorithm which will start at different nodes and do different work, right? So that's the model where like your algorithms are expensive, you want to, but graphs fit. And
Yeah.
You will like if there is no work sharing essentially. Like if you need parameters, intermediary steps from one algorithm to the other, you don't communicate them, right?
Yeah. So this is only for the embarrassingly parallel algorithms,
Okay.
like the all pair shortest path stuff. Any other questions? Okay, cool. Thank you.